Okay, so last time we ended with this given equation where we wanted to compute del z tilde del v, which we formulaically saw was del g del x del v plus del g del y del v plus del g del v. And we also were given that x was u e to the v and y was u squared e to the minus v. And so we compute just term by term. So del g del x is 12x squared y e to the v plus 4x cubed 2u e to the minus v. That's the first term right here. I'll try to label each term. Del x del v is u e to the v itself, plus, and then there's del g del y, which is the following. We have 4x cubed e to the v plus, and then in the for y we have basically this product that we're looking at. So we end up with 4u e to the minus v. The x to the fourth term goes to 0, and that's this del g del y term, times del y del v, which is negative u squared e to the minus v, and plus, let me write the last term here so it can all be seen on one screen, plus the last part, which is del g del v. And del g del v is 4x cubed y e to the v, because the derivative e to the v is e to the v, and 4x cubed y is a constant as compared to when we're taking derivative strictly in the v direction, plus, it becomes a minus here. The whole term stays, but because there's an e to the minus v, we get a minus x to the fourth plus 2y 2u e to the minus v. So this term right here is the del g del v. And this overall is the partial of z tilde with respect to v. And of course, if we wanted to plug in a particular value, we would, you can plug in uv equals 2, 0, and respectively you'd have to plug in x of 2, 0 and y of 2, 0 to get the partial at 2, 0. To get del z tilde del v, which was del squared z del v del u at this particular point at 2, 0. Okay, so this was just again another exercise in taking partial derivatives. So that's what we get. Now there's one last piece which I want to talk about, which is all about implicit differentiation. And I'm not going to do both versions. There's essentially the version that you already know. That's the version we're going to look at, which is, so if you're given capital F of xy being 0, so you have it implicitly, so it turns out that under certain conditions, and those conditions essentially are the partial derivative of y should not be 0, and the partial derivative in the x and y direction should be continuous, If these are true, and we're usually centered at some particular point, but there's a theorem called the implicit function theorem, but that says that then y is actually a function of x near a particular point. So what if you're given a general like a implicitly defined function y of x? So essentially here this means f of xy is actually, this equation can be replaced with f of x, little f of x, where y is little f of x. So in this situation, that's true. So, but if you're generally given such a condition, the question is, what is dy dx? That's the question of implicit differentiation. You can also do this with more variables, x, y, and z. We're going to just skip that portion, but it's very similar. So we're just going to do this part. How do we do it? Well, here's our little diagram. F depends on x, and f also depends on y, which also depends on x. So we want to find the partial derivative, oops, not d, but the partial derivative, d by dx, del by del x of f so let's call z, again, notationally, it's always a bit challenging here. So let's call z to be this capital F of xy, which is 0. So we want to find del z del x. Well, what is that? It's the partial of f with respect to x. And then x, well, I mean, x is an independent variable, so you could write dx here, I suppose, because x, I guess, depends on itself if you wanted to really be, totally complete. But that's just 1. You can kind of omit that. Plus del f del y, and then there's dy dx, and all of that equals 0 because, well, the whole thing, it's an implicitly defined function. We've set it equal to 0. So essentially we have del f del x plus del f del y times dy dx is equal to 0, or just to make the notation a bit compact, we have f sub x plus f sub y dy dx is equal to 0. So if you solve for dy dx, you get negative fx over fy, which is negative del f del x divided by del f del y. So this is the implicit differentiation rule, or formula, I guess, to find dy dx. Let me just circle it because that's an important one here. And let's just do one example. So let's say we have x cubed plus y cubed is equal to 10y. And we want to find, let's say we want to find an expression for dy dx. Let's do it 2 parts. And let's say we want to find the equation of the tangent line at, say, x equals 0. So then, and here, let's change that part here. At x equals, well, let me omit that part for the moment. We'll come back to that a little bit later. Let's just find an expression for dy dx. So first off, how do we convert this into a problem where we have a capital F of xy? Well, notice that this is just x cubed plus y cubed minus 10y is equal to 0. So, well, what do we have then? We have f of xy is x cubed plus y cubed minus 10y. So partial of f with respect to x is 3x squared. Partial of f with respect to y is 3y squared minus 10. So, well, I guess we can actually, so notice, so the reason why I didn't want to do the finding the expression of the tangent line yet is because I have to check some conditions on these. Well, notice here that dy dx is negative 3x squared over 3y squared minus 10. So the condition actually from the implicit function theorem, which just is kind of obvious from this formulation, is that the denominator here can't be 0. Denominator is not 0. Okay. So let's find the equation. So let's do a part B. Let's find the equation of the tangent line at x equals 0, and let's also have y be 0. So what would that look like? Well, first off, note that that satisfies the original equation, that f of xy, so first, note that capital F of xy equals 0 at x equals 0, y equals 0. So it satisfies our equation. We have to first check that. Well, and now all we need, we have a point, 0, 0. All we need is a slope. Well, what is our slope? Our slope is dy dx. And that's 0 over 0 minus 10. So our slope is 0. If our slope is 0, then the tangent line, well, it still works by the same formulation. Y minus y1 is m times x minus x1. So we simply get the line y equals 0. So this is a place where the tangent line is horizontal. In particular, the tangent line is exactly the line y equals 0. Okay, so this is an example of implicit differentiation, and we're going to conclude here. This is the end of 14.5, and we will start 14.6 in the next video.